I will be reading The End of Employment, Part 3 by John Michael Greer. A principle that ecologists call Liebig's law of the minimum is relevant here. The amount of anything that a given species or ecosystem can produce in a given place and time is limited by whichever resource is in the shortest supply. Most people get that when thinking about the non-human world. It makes sense that plants can't use extra sunlight to make up for a shortage of water, and that you can't treat soil deficient in phosphates by adding extra nitrates. It's when you apply the same logic to human societies that the mental gears jam up, because we've been told so often that one resource can always be substituted for another, that most people believe it without a second thought. What's going on here, though, is considerably more subtle than current jargon reflects. Examine most of the cases of resource substitution that find their way into economics textbooks, and you'll find that what's happened is that a process of resource extraction that uses less energy on a scarcer material has been replaced by another process that takes more energy but uses more abundant materials. The shift from high quality iron ores to low grade taconite that reshaped the iron industry in the 20th century, for example, was possible because ever increasing amounts of highly concentrated energy could be put into the smelting process without making the resulting iron too expensive for the market. The point made by this and comparable examples is applicable across the board to what I've termed technic societies, that subset of human societies, ours is the first, though probably not the last, in which a large fraction of total energy per capita comes from non-biological sources and is put to work by way of machines, rather than human or animal muscles. Far more often than not, in such societies, concentrated energy is the limiting resource. Given an abundant enough supply of concentrated energy at a low enough price, it would be possible to supply a technic society with raw materials by extracting dissolved minerals from seawater or chewing up ordinary rock to get a part per million or so of this or that useful element. Lacking that, and there are good reasons to think human societies will always be lacking that, access to concentrated energy is where Liebig's law bites down hard. Another way to make the same point is to think of how much of any given product a single worker can make in a day using a set of good hand tools, and comparing that to the quantity of the same thing that the same worker can make using the successive generations of factory equipment, from the steam-driven and belt-fed power tools of the late 19th century straight through to the computerized milling machines and assembly line robots of today. The difference can be expressed most clearly as a matter of the amount of energy being applied directly and indirectly to the manufacturing process. Not merely the energy driving the tools through the manufacturing process, but the energy that goes into manufacturing and maintaining the tools supporting the infrastructure required for manufacturer maintenance, and so on through the whole system involved in the manufacturing process. Maverick economist E.F. Schumacher, whose work has been discussed in this blog many times already, pointed out that the cost per worker of equipping a workplace is one of the many crucial factors that mainstream economic thought invariably neglects. That cost is usually expressed in financial terms, but underlying the abstract tokens we call money is a real cost in energy expressed in terms of the goods and services that have to be consumed in the process of equipping and maintaining the workplace. If you have the energy to spare, that's not a problem. If you don't, on the other hand, you're actually better off using a less complex technology, what Schumacher called intermediate technology, and the movement in which I studied green wizardry 30 years ago called appropriate technology.